this video, we will talk about an important concept in integral calculus, Riemann sum. Before we actually talk about Riemann sum, let's first introduce the sigma notation. The sigma notation has three parts. The sigma itself, which stands for sum, or you add them together. At the bottom, there is I equals to 1, which means we start with when I equals to 1, and we stopped at when I equals to n. In other words, this can be expanded as a 1, because when I equals to 1, plus a 2, plus a 3, and all the way till when I equals to n, which is a n. For example, if I have sigma when I equals to 1 till 5, and I have, let's say, 1 over I, that's my I, then this can be expanded as when I equals to 1, which is 1 over 1, plus when I equals to 2, when I equals to 3, all the way till when I equals to 5, so that's going to be 1 over 4 plus 1 over 5. Okay? Also notice that we don't have to start with 1 here, you can start with any of the integer, but my I should always be integer. We have some properties of sigma notation. Let a1, a2 all the way till an, and b1, b2 all the way till bn represent two sequence of terms, and let c be a constant. Then the following properties holds for all positive integer n and for integers m, while my m is bigger than or equal to 1 and smaller than or equal to n. The first one we can see that is if I have a constant here instead of ai, then this is the same as n times c. We don't have to memorize it because, well, what should make sense to you, consider you have, let's use a specific c here. So consider you have a summation from 1 to n, and I have a constant here, let's say 5. Okay? And we can expand it. What does this mean? This means that I'm going to add 5 n times. And I have n times here, and you know that this is equivalent to 5 times n, right? So this is what it means. Notice that the c does not have to be a specific number, so sometimes you can use like a variable as long as it's not going to change when I changes, then we consider it as a constant. For example, so another example here, what you'll probably see the most is if I put n here, what's gonna happen? So I'm gonna add n, where n is a natural number. I'm gonna add n to itself n times. Okay? This is still, because n is a specific number, although we don't know what it is, it's still adding to itself n times, so we know that this is basically n times n, or n squared. So what I want to point out here is c does not have to be a specific number like 5 or 10. It can be a variable like n, as long as it doesn't have I involved. Next, we have summation of c, a constant, multiplied by ai. And this is equivalent to, you can take this c out of the summation notation, and they are the same thing. So again, you don't have to memorize it. Let me explain why it works. Because the first part is basically, I guess I'll still write it properly, is basically ca1 plus ca2 all the way till can, right? And now, since every single term has a common term c here, we can actually factor it out. So that's the same as c times a1 plus a2 all the way till an. And what's in the bracket, this summation can be rewritten as sigma notation. So this is the same as c times summation from, I just noticed it's from m, not from 1, but 1 also works. So let's change it to m. Then it will be m plus 1 here. M plus 1 n plus 1, and all the way till 1. So that's gonna be when I equals to n till n, ai. Okay, so you can see that the left hand side, which is this, equals to the right hand side. All we did is factor out the common constant, which is c, because it's not changing. But again, here the c does not have to be a specific number. Again, it can be a variable. So if I put n here, for example, it still works. Okay, I can put b here, whatever variable you would like, as long as it doesn't change with I, then it's okay. So we can always factor it out. Number 3, it's saying that, well, if you, instead of the summation, you have two terms adding or subtracting to each other, then you can split it up to two summations. Again, you don't need to memorize it because it should make sense to you. I equals to m all the way to n, ai plus or minus bi. If I expand it, this is the same as am plus bm. That's the first term, and then plus, see, I really need more space, plus am plus 1 plus bm plus 1, and all the way to am plus bm. Right, that's the left hand side if I expand it, but notice that I can rearrange it. Okay, I can add the a's together first and then add the b's together next. So let me rewrite this. That's gonna be am plus 1 and all the way till an. So that's the first part. We can put in bracket. Plus, and then let's add all the b's together. bm plus 1 and all the way till bn. Okay, and you can see that, well, this part is exactly two summations. So sigma when I equals to m till n ai plus sigma when I equals to m till n bi. Okay, so you can see that 1, 2, and 3, they should all make sense to you. You don't have to memorize them, and sometimes you need to combine them together when you use them. And you should be very familiar with them because later you'll use them over and over again. We'll see an example very soon. Number 4, 5, and 6. Let's talk about 4 first. 4 is basically saying, well, if I add each of the number consecutive integers together, so start with 1, so this means 1 plus 2 plus 3 all the way till n is basically n times n plus 1 over 2. If you finished Math 102, you can prove those 3 easily using induction, and I believe some of you probably have proved number 5 in your homework or something, so you know that they are true. For number 4, let me show you something interesting. So consider I have a bunch of balls. Specifically, I have n of them. Okay, so suppose I have n of them. I know right now it seems I have only 1, 2, 3, 4, 5, 6 of them. It's gonna be like 6 by 6. Okay, I guess I just copy paste. So let's say I want to count how many are there, how many balls are there. But this is 6 times 6. We have 36 of them, or n square of them. That's not really what I want. So what I really want to do is I want to count the number of balls in this part. So why is this the same as this? Because you can see that maybe I'll rotate it a little bit to show you. So if I rotate it a little bit, you'll see that my first row I have 1 ball, second row I have 2 balls, third row I have 3 balls, fourth row I have 4 balls, fifth row I have 5 balls. So if I want to count the number of balls here, that's basically 1 plus 2 plus 3 plus 4 plus 5. Correct? Which is what I want here. So the n here would be 5. Okay? So that's one way to count this. The other way I want to count this in a different way, right? Will be how we got this. the other way, how do we get the number of bars here? So let me rotate it back so we can see that the other way to count it is I can consider the whole thing first. So I can count the whole thing first, which is gonna be the whole thing, which is gonna be n plus 1 square, right? Because here n is 5, but I have 6 times 6. But now I don't just have n plus 1 square because, well, I cannot just divide by 2 because you can consider as 3 parts, thus the main diagonal and another copy of this, right? So because of that, this is basically, I need to minus the main diagonal, which has n minus 1 of them, and then I can divide by 2 because, well, after I remove this part, it's exactly half of what's left. And once you simplify this, you can factor out n plus 1 first. Factor it out. The first part has n plus 1 left, the second part has 1 left, over 2, which is exactly n times n plus 1 over 2. This method is called combinatorial proof, or count in two ways, geometrically showing you that this is true without induction. Alright, I think for this one, if you want to show it geometrically, it's going to be a lot harder if you don't know combinatorics. So for those of you who know induction, just try to prove it using induction. If you don't know, then maybe you can search it up, a proof for this if you don't know induction. But they are all true, and you can prove them easily using induction. I'm going to move on, but you should know all of those, okay? 4, 5, and 6 are used pretty frequently when you do Riemann sum and definitely integral. Now, let's look at an example of using the above. And you need to know a little bit of limits from the course you took before, either it's 135 or 132 or whatever differential calc you finished. But let's have a look. Before we deal with the limit, let's just simplify what's here first, because, well, it looks very complicated, right? So let's simplify it first. I'm gonna copy down the limit part, and I have a summation of this whole thing. First step is I'm gonna try to simplify it first. So this 2 over n, I'm gonna leave it like this. So 2 cubed is 8i cubed and n cubed plus, and I'm gonna multiply it inside, so that's 10i over n. Okay, once you do this, I can see that, well, I can put this in so that I only have 2 terms. When I have 2 terms adding together, I can split them up to be 2 summation, right? So there are a few things I can do. If you don't want to split them up, you can also take out some of the terms. So now I have, I can put this in, so I have 2 terms, and I can make it 2 summations. So sum of I equals to 1 till n. And then I want it to be 2 terms, so multiply them together. I have 16i cubed over n to the power of 4 plus 20i over n squared. Okay, and as I mentioned, well, now I have a summation of 2 terms adding together. By property 3 here, I can split them up into 2 summation. So let's do that. So I can change it to 2 summations. Here I'm doing it step by step. So if you are familiar with it, you can do maybe multiple steps at the same time. But since we are just nerding it now, I'll do it step by step in case anyone cannot follow. 20i over n squared. Okay, here I use the property, so I'll write it here. This is by the property sum of 2 terms. Here I use a plus version, so I'm only gonna write the plus version. ai plus sigma I equals to n bi. So this is a property I used. Now I have two summations, okay? And you know that, well, I have other things I can use. So we can see that, well, I want to simplify this term, I want to simplify this term. You can see that, well, at the bottom here, this n to the power 4, and at the top here, the 16, they are basically constant in this case. Because, well, they're not going to change when I change, right? They're not going to change when I change, so I'm going to highlight them here and here. They're just constant, so I can take them out from the summation, right? And also, in this term, this n squared and this 20, they're not going to change when I change, so they're constant as well, so I can take them out from the sigma notation as well. So let's do that. The first term, I'm going to be left with IQ plus the second term is 20 over n squared, summation from 1 to n, and I'll be left with I. And here, I use the second property where you can take out or factor out the constant. Next, I noticed that, well, I have a formula for this, right, for IQ. I also have a formula for I, for just like adding them together. Oops. And they're right here. They're right here. So I have this formula. I also have this formula, so I can use them, right? So let's use them. Let's use the two formulas I know. Then I'm gonna be left with 16 over n to the power 4 multiplied by n squared times n plus 1 square, over 4, because that's my formula. In case you don't remember, I'll let you see again. And then plus 20 over n squared multiplied by n times n plus 1 over 2. Alright, and now we can simplify, because, well, there are terms you can cancel out, so let's cancel out some of the terms. And so this n square and this n to the power 4 can cancel out with n square at the bottom. This 16 and this 4 can cancel out with a 4 here left. Similarly, in the second term, this 20 and this 2 can cancel out with a 10 left here. This n and this n square can cancel out with an n left there. So after cancellation, again, I can write down my final result here. Will be, let's put them all together actually. So at the top, I have 4 times n plus 1 square left. At the bottom, I have n square left for the first term, plus the second term. At the top, I have 10 times n plus 1 left. At the bottom, I have n left. Okay? And now you can simplify more if you want. Well, but you don't have to. You can compute the limit directly if you know how to. But I'm going to simplify it a little bit more so that it's easier for you to compute the limit. So let's do it. What I'm going to do is, well, this is basically n plus 1 over n, the whole thing squared, right? So I can change it to n plus 1. Okay, so let me change it a little bit so it's easier for you to see. It's basically 4 times n plus 1 over n, the whole thing squared. In this case, well, definitely I can simplify it because, well, this can be rewritten as 1 plus 1 over n, and then the whole thing squared, right? Why do I do that? Because it's easier for you to compute the limit. Well, you don't have to do that, but only doing it so you know what's the limit, because some of you are not very strong at computing limit. Similarly, this term can be rewritten as 10 times this over this, which also can be split to 2 fractions. So 10 times 1 plus 1 over n. Okay, so why do I do that? Because, well, we know that as n goes to infinity, this term is going to be 0, right? This term is also going to be 0, so what's left is easy for you to see. Alright, so let me write it down. As n goes to 0, this is gonna be 0. I mean, goes to infinity, this is gonna be 0. This is also gonna be 0. So what's left for you after computing the limit is just 4 times 1, which is 4, plus 10. So my final answer is 14. Oops. Okay. And technically here I should write down what I used here, so should I? Whatever. But I'm saying that in the step I used this and this. Okay, I'm too lazy to write it down. But technically I should write it down. But you know what I used because I highlighted them. So this is an example for you to show how we use the above properties. They are useful. We learn Riemann sum and definitely integral. You'll see something like this again. Well, once we reach definitely integral, you'll see. So useful, good to know.